Okay, there we go. We're recording. Okay, so welcome to Math 219. Let's see here. So glad to have you in the class. All of this stuff about the sort of course organization, how to do well in the course, what is this course about, that kind of stuff. I've already talked about in that recording that I made and sent to y'all last week. So I'm mostly not going to go over this again, but I do want to emphasize, be sure that you watch that recording, pay attention to it carefully. There's a lot of important stuff in there. And don't forget, the Sakai sites, both of the Sakai sites, make sure to read them thoroughly. A lot of critical information about how the course is organized, how to do well in the course, etc. A bunch of that kind of stuff. Okay. All right. I do, though, want to say a couple of quick things about the course organization that I think I may have forgotten to mention in the recording. So specifically, you'll notice now I'm on our section Sakai site here, and if you come down here to the let's see, this is the course grades tab, and I think I failed to actually note specifically that. In addition to the course requirement, that all the midterm weights add up to 60%, specifically in my sections, there'll be 20% apiece for the three midterms. Okay. And then also, for the course requirement of 10% weight attributed however the instructor sees fit, I'm making 7% of the course grade homework and 3% attendance. Just about the attendance real quick, I'm not going to start counting attendance this week because the course roster is going to be in flux and people are going to be moving between sections and the other instructor, and it's going to be a nightmare of confusion. And so I'm not going to start it this week. But next week, I'm not sure if I'll start on Monday, but sometime next week anyway, we'll start taking attendance. And I'll be calling names, visually checking that you're here, etc. Eventually, I will learn your names, and I'll just be able to, check them off as you come in. But until then, I'll be calling names. Usually takes me 3 weeks, something like that. Okay. All right. So, any questions? Let me say any questions about any course organization stuff before we get into math. Okay. All right. Well, good to have you here. One thing that occurs to me, and maybe I will also say, you'll notice I'm wearing a mask per the requirement. I notice many of you are not. I'm also going to notice that I am under no obligation to police any requirements about masks. So don't feel any pressure from me. The university has its own rules, of course, and y'all follow as you see fit. I don't pay attention to the requirements that they put on students, just the requirements for me. Okay. All right. So, so let's dive into some math. Let's see here. So, Okay. So the first thing I want to talk about is, why are we here in a multivariable calculus class? That is, why is multivariable calculus important? Why are you taking a multivariable calculus course? So I'll start by saying I know that for many of you the answer is because my major requires me to take a multivariable calculus course. So let me rephrase then, if that's the case, why does your major require you to take multivariable calculus? What is it good for? So I'm going to start by assuming that you already have bought into the idea that single variable calculus is important. Hopefully your single variable calculus courses have been persuasive on this. If not, just, broad strokes. If you want to understand how things change, how, quantities, that's a big tent, right? How do quantities change? Well, that's derivatives, right? So calculus is important if anything anywhere is changing. So that's a pretty big application. So there's one. The other thing, integrals. Now, integrals, a lot of students, I'm going to say, misunderstand and think that integrals, the purpose of an integral is to compute the area under a curve. It's not really. It's actually pretty rare in practice, in application, that what you fundamentally deep down really need, underneath it all, what you need to know is area under a curve. It's pretty rare, actually. It happens to be that the things that you need to compute are computed by methods that coincidentally, as it happens, can also be thought of as also computing areas under curves, right? It was kind of a coincidence, really. So in general, what we're interested in is what I like to call accumulating quantities. Things which, if you chop up the question into smaller pieces, you can just look at the question on the individual small pieces and then add them up. So for example, y'all have all seen the single variable calculus example of mass of a rod, right? So you have I'm going to say a one-dimensional rod, but something that we keep track of in terms of length, where mass is mostly just in one direction, right? And suppose that the density varies, and so maybe the mass per unit length over on this side perhaps is higher, and the mass per unit length maybe in the middle is lower, and then over on this edge is maybe higher again. I don't know. So if mass per unit length varies, you want to compute the total mass. Well, you can't just multiply mass per unit length times length, because the mass per unit length varies. It's not a constant. It's not well defined. So what you can do, though, is you can take that rod, you can chop it up into little pieces, right? And on each little piece, you have an easy question. On each little piece, the mass per unit length is approximately constant. On each little piece, you multiply mass per unit length times the length of that little piece. But then the key point, the thing that allows an integral to work, what makes this an accumulating quantity, is that when you're interested in the total mass, you can view that as the sum of the individual pieces of mass. Right? So yes, you can use an integral to compute the mass of a rod because that's an accumulating quantity. Right? And now y'all have seen a bazillion examples in single variable calculus class of how we use integrals to answer practical questions. And so I'm going to say they all classify as we're computing accumulating quantities. Okay. Alrighty. So single variable calculus, again, old news. Hopefully you're already on board. So here's the thing. Single variable means one-dimensional. The world is three-dimensional. It's not one-dimensional. And so, short answer, why do we learn multivariable calculus? Because we live in a multivariable world, right? And so it's really not shocking at all. Now, some easy examples of this. Suppose we're thinking about how temperature varies. In the three-dimensional world where we live. Well, temperature depends on position. It depends on X, Y, and Z. The temperature up there and the top of the room next to the window where maybe there's some heat coming in for, it's a hot day outside, and heat rises, so up high it's probably warmer. Probably warmer up there than it is, down there in the bottom corner in the shade, much cooler location, right? So temperature varies throughout the room. It's probably warmer over here. It's probably warmer next to the bulb there of the projector, that kind of thing, right? So temperature is a function of three variables, X, Y, and Z. So reasonable question we could ask then is, suppose that I'm here and suppose that I am moving in some direction with some, velocity. So that all three of these variables, as I move, they're all changing. I'm moving somewhat upward, somewhat in the Y direction, somewhat in the X direction. All three of the variables are changing. How do I compute the rate of change of temperature? Well, this is not a single variable calculus problem. There's three variables. Right? So, in order to answer questions like this, and we're not going to answer the question today. We're going to develop various tools and techniques, and we'll get to it eventually. But in order to be able to answer this question, we're going to be doing necessarily multivariable calculus. Does that make sense? Okay. All right. All right, here's a kind of a three-dimensional version of the mass of a rod question. I'm going to call this the mass of a lump question. All right, honestly, a little bit more physically relatable. I mean, when you think about mass, it usually comes in the form of lumps, right? A bunch of rocks I have in my backyard, they look more like this than they do like a one-dimensional, straight rod. So, okay, well, density, mass per unit length, density, mass per unit volume, since we're talking about mass distributed over a volume, is going to depend on location. Maybe it's really dense up here where there's an iron, heavy iron deposit, and then maybe less dense, over there, and then maybe there's really, really low density region in there, and then maybe a little bit more density there, and maybe a little bit of higher density there. Right? Density varies dramatically throughout the rock. So grand total, what's the mass? Well, it's not a single variable calculus problem. You can't answer this with single variable calculus. What we're going to have to do is figure out how to take this problem, capitalize on the fact that, again, mass is an accumulating quantity. I can take this rock and I can chop it up every which way into a bunch of teeny tiny itty bitty little pieces. And on any given little itty bitty teeny tiny little piece, I can say, you know what, on that little piece, the density is approximately constant. I can talk about mass per unit volume, multiplied by the volume of this little piece. Easy questions on the teeny tiny pieces. And then I've got to figure out how in the world do I add that up over an entire lump of a rock. Right, so this is going to be another multivariable calculus problem. Unavoidably multivariable. Can't do this with single variable calculus. Okay, so the world's three-dimensional. So pretty easy pitch that we're going to need. If you want to use the ideas of calculus in a three-dimensional world such as ours, pretty believable you'll need at least multivariable through 3 dimensions. Is that cool? All right. Okay, now here's another example. This is an econ example appropriate, I suppose, to the fact that we're in their building. But here's what I'm going to call an economic model, and I just made this up. The model itself that I've got written down here is not what's important. The point is, economic models tend to come in the form of, well, you write down an equation, possibly several equations, but let's keep it simple. Let's say an equation that involves a bunch of variables. So price, quantity, interest rates, capital, labor. If you're making a small business or something, then these are the kinds of things that you're going to be dealing with. So you make an equation that involves these, and this describes all things considered, this equation has to hold. And again, this is called an economic model. So suppose then that subject to this economic model, suppose we know how some of those variables are changing. And we'd like to know how the remaining variable is changing. How are we going to do that? It's tempting to say, let's solve for that other variable. We'll solve for p. And then we'll take its derivative. How about that? But here's the thing. I can't solve for p. Look, we've got a cubic issue here. Worse than that, we've got a transcendental problem here. You cannot solve for p. That's not an option. So, how are we going to be able to relate within this model? In other words, given this equation, how are we going to be able to relate the rate that I'm interested in to the rates that I know? Okay, well, so there's another multivariable calculus problem, and we're gonna answer this question. Again, it's going to take us a while to get to this, so no rush. But the reason I like this example, 2 reasons. First of all, this is a non-physical example, right? This is kind of, you might call it an abstract example. We're not, there's nothing viscerally physical that I can point to or, tap with my finger, what have you. It's abstract. But the other thing I love about this example is it's high dimensional. So you can see right here, we've got 5 variables. you could argue that there are kind of 6 variables here because you're taking derivatives with respect to time. So depending on how you want to look at it, and just to avoid the ambiguity, sometimes we say 5 plus 1 dimensions, indicating that, depending on how you want to think about it, you can interpret that either way. But it's definitely not 3-dimensional, right? So notice there's nothing particularly sci-fi, fantasy land, the 4th dimension. Are we time traveling? Nothing creepy in this example. It's just economics. We're running a small business, right? And yet, even in this very real world kind of a situation, we already need more than 3 dimensions. So I want to dispel this idea that we live in a 3-dimensional world and therefore we'll never need more than 3 dimensions. This is not true. So we're going to need beyond 3. And the thing about it is, it's hard to draw pictures. So in this class, just so you know, we're going to focus very heavily on 2 and 3 dimensions. But every so often, we're going to need to be able to write some things down in higher than 3 dimensions. And here's the other good news. The way we will write things down, the calculus of 6 dimensions, it's actually not that different from the calculus of 2 or 3 dimensions. So we kind of, in some sense, don't have to worry about that too much. Okay, how are we doing? Everybody on board? Okay. All right. So just kind of for fun, we'll do this physics example, and it's kind of scary looking when you write it down on the page. So these are called Maxwell's equations. Y'all might have seen these previously in a physics class, conceivably. They describe how electricity and magnetism work. At least they describe certain aspects of how E and M work and how they relate to each other. These are certain facts about these vector fields. And so if I want to understand E and M, if you're an engineer or a physicist, even to some extent if you're a chemistry major, you need to understand Maxwell's equations. So you're going to need to understand all this stuff, which means you're going to need to understand what that means. What is that symbol right there? Right? And then even weirder, perhaps, what is that thing? It looks like a differential, but it's got a vector hat over it. How does that work? That seems weird. Right? A differential, that's a vector? Wow, strange. So we're going to need to understand that, and we will. This is some stuff we're going to get to. It's going to be near the end of the course. This is kind of chapter 7 kind of stuff. And we'll start getting into this kind of thing in chapter 6. But so that's yet another application that's really, really important, electricity and magnetism, that we're gonna study. Furthermore, not just the individual objects in these equations, but what is this equation as a whole really saying? And what's the best way to think about this state? What does that statement look like? What's the picture that this is basically summarizing? Right? So those kinds of ideas are other things that we're going to spend a lot of time thinking about, and we want to make sense out of this more fully, and not just understanding the individual pieces of it. Okay. All right. Pausing again for questions. Real quick, I will point out that it's going to seem weird, but this equation and this equation are largely considered to be the same equation. Obviously, they're not exactly the same, but they're from a certain point of view. And when you understand these geometric perspectives that I'm talking about, that we're going to develop, in learning multivariable calculus, we're going to learn how to think about this equation. When you know how the right way to think about this equation, what will follow is that in fact these are really largely the same equation. So that's something to be on the lookout for. And when you get to that point, where you can see how these equations very closely connect to each other, you're going to have a tremendous advantage in E and M. So specifically, some of y'all have already had your Duke E&M course. But for those of you who haven't, if you take this course first and then subsequently take E&M, you're going to have a massive advantage. Because a lot of E&M is just trying to make sense out of this calculus. So if you have that already done, you're way ahead of the game. Okay. All righty. Pausing. Questions? Okay. All right. So back up to the, why is multivariable calculus important? Well, it's we live in a three-dimensional world, so of course. There's things that we need to do that are in higher than 3 dimensions. There's applications to physics and engineering. I mean, extremely strong applications to physics and engineering. And here's another one. I've listed this as an application to chemistry and physics. I mean, in some sense, we've already seen a nice application to physics. So let's focus on the fact that this is a nice application to chemistry. And specifically, I want to talk about Schrodinger's equation. So this is it. This is one of the central equations of quantum mechanics. And I'm sure you all have all heard of quantum mechanics. And exactly what it is that's a whole course, couple of courses. It's a whole field of study. But being able to solve Schrodinger's equation is one of the big deals. In particular, molecular bonds. I mean, there's some chemistry for you, right? The bonds within molecules between atoms. They come from the behavior of electrons, and electrons, their behavior is described by Schrodinger's equation, right? So now what does this have to do with multivariable calculus? Well, this operator here, it's called the Laplacian operator. This operator is made up out of objects of multivariable calculus. This thing, the Laplacian operator, is really fundamentally an object of multivariable calculus. So, as a whole, this equation is referred to as a partial differential equation. And y'all will, in your math, let's see, those of you who are engineers will eventually take Math 353, and you'll see how to solve some PDEs. I don't know if they do this or maybe some special cases of this. I'm not sure. But that we're not going to do that in this course. But nevertheless, this object is an object of multivariable calculus. So, if you take a PChem course, any chem majors taking a PChem course, then that will, in that context, you'll see this equation. Okay, any questions about any of that? So I think this is a lot of examples. I hope I've been persuasive that why is multivariable calculus important? Why are we here? Why does your major make you take this class? The way I like to summarize it is that multivariable calculus is the calculus of the real world. Right? In some sense, all of let's not overstate it, but a lot of single variable calculus kind of quietly assumes that certain very nice conditions hold that allow us to take a real-world problem and deal with only one dimension of it. Right? And so that's sometimes even natural. But very often it's not. Very often the real world is messy and depends on all of the variables. And thus, here we are. Okay, pausing again. What do you think? Everybody buy it? Okay, so moving along then, we're going to go into chapter 1. Real quick, and I already talked about this in the initial recording that I sent to y'all last week, but there's a tremendous amount of material in this course. When I set up my lectures for the class, I'm not gonna, take the book and go from, the beginning to the end of each section. There's way too much stuff. There's stuff that I want to talk about that's not in the book. I want to give you, extra perspectives, things that I think will be useful. I'm going to be making my decisions about what to cover based on what do I think is going to be the most useful to you over the course of the semester, right? So there's going to be some stuff in the book that's, It's review. Stuff you already know. And that's not a good use of class time to go over and spend a bunch of time talking about things that you already know. I mean, now sometimes we're going to do a little bit of this right now. There will be things that you've already seen, but that experience shows that a lot of people are rusty on, and it's sufficiently important that I feel like I've got to say some things about it. So there will be some review here and there, but there will be a lot of stuff that I'm going to say. It's in the book, that's eminently readable, and give it a look, and come to office hours if you have questions. Okay. All right. So chapter 1, we're going to move really fast through chapter 1. It's a lot of it is review, either review or things which you've already got a lot of the tools for. So we are going to spend some time in chapter 1. I've already forgot. I think we're going to spend a week or so here in chapter 1. That's the goal, anyway. We'll see how fast we actually move. But a lot of it is review. So I'm going to say, you've seen most of this already in linear algebra. Okay. I like to do section 1.6 first. This has got some stuff in it that's really, really handy for everything else that we're going to do. And so I like to get it done as soon as possible. Anyway, here we go. Let's start with the triangle inequality. Hopefully you've seen this before. If you haven't, it's a pretty believable statement. What it says that if you add vectors, you all know how to do that, then the length of the sum, namely that distance, is less than or equal to the sum of the individual lengths, which is that distance. Or you might view this as saying, if you look at different paths between 2 points, the shortest one is the straight line path. So, well-known fact of geometry of flat space, the shortest distance between 2 points is straight line. Is that good? Okay. All right. Good. By the way, how to prove this fact is a problem in linear algebra. And you might entertain yourself by trying to remember how that works. Or if you haven't seen it before, play with it. I think it's in the book, by the way. But if not, it should be in your linear algebra book. Okay, matrix multiplication. Now, I know y'all know how to multiply matrices. All too often, in high schools especially, they focus on, which of the several equivalent formulas for matrix multiplication allows us to compute stuff the fastest and most effortlessly. And so that gives rise to the old formula that I'm sure you've all seen, which is, you look at the rows of the left matrix and the columns of the right matrix, and you dot the rows of the left with the columns of the right. And those dot products gives you elements of the product. So that formula is very computationally useful, if that's what you need. If performance of arithmetic is your what you're here for, right? And usually, though, in practice, it's just not what we need. I mean, we've got computers. Computers are really good at that sort of thing. Right? So we're here to do mathematical thinking. We're here to understand connections between different objects of natural geometric interest. And that formula, it turns out there are some circumstances where that actually connects some important ideas in interesting ways. But most of the time, that's not the best one. This point of view here, I think, is more often a connection between important objects, important ideas. We're going to see a great example of this on the next, in a couple of pages. So let me remind you what this says. This says a matrix vector product is a linear combination. There it is, matrix vector product, a linear combination. It's a linear combination of the columns of the matrix. As you can see here, A1 through AN, where you can literally see we're taking a linear combination of the columns. There it is. And specifically, which linear combination? Well, the one where we use the vector, more specifically, the coordinates of the vector, as your coefficients. So now this does not, at a quick glance, look exactly like the dot product formula. It turns out, and it's a pretty easy thing to observe, if you put some numbers on the page, write down some actual matrices and start doing the actual arithmetic, you're going to notice that the arithmetic you do in this formula actually is pretty reminiscent of the dot product arithmetic. It's just a little bulkier in how we write it down, so it's a pretty easy pitch to believe that this is true. But what I like to point out about this is drawing connections between objects of natural interest. So in particular, this is a relationship between matrix vector multiplication, linear combinations, which of course we know is a natural construction, column vectors. Right? That's pretty interesting. So these are mathematical objects that are being related by this formula. And that just makes this actually really useful, and I think significantly more often than the dot product high school point of view on matrix multiplication. So anyway, I imagine you've probably seen this in Math 218, but I just want to make sure, and I want to make sure everyone review a little if needed, but make sure that you're really comfortable with this point of view on matrix multiplication. Okay. Are we good? Okay, linearity. So I know you all heard the word linear. I know you all have done a lot of stuff with linearity. Experience shows, though, that a lot of students maybe never really quite digested exactly, precisely what does linearity mean. And so this is another really important thing. So just want to make sure we get this settled. What it means for a function, we're going to focus our attention on Euclidean functions, by which I mean functions that have Euclidean, namely Rn, domain, and Euclidean targets also. So I'm going to call these Euclidean functions. So a function is linear if it has this property right here, which I like to think of as putting a linear combination in before you apply the function, doing the linear combination after you've applied the function. Either way, you get the same thing. Right? So this turns out that there are just extremely powerful things that you can say about functions that have this property. They're just crazy useful and super common and useful thing to understand. So anyway, this is what linearity means. Side note, this condition here is equivalent to this pair of conditions, and it is also equivalent to this condition. So take your pick. My personal picks tend to go like this. If I need to prove something, I like working with this characterization of linearity because it's only one condition and there's only two vectors involved. And I feel like that's makes it very desirable. So if I need to prove something, if I need to pick one of these to be a liability, I want the most compact liability, and I think this is that one. If I'm going to use linearity, if I've been told that I have a linear transformation and I want to, hey, what do I get out of this deal? I like this one because this allows any number of vectors, and that's really neat, really useful. Okay. All right. So a couple of examples, and you might have seen these before, you might not. Part of my motivation in picking these examples is that they are examples. The other part of my motivation is that I think these are of particular interest, and I want to make sure that y'all know specifically that these specific functions are linear. So first one, got a function here called P. It's defined by, we're going to fix a vector A and do dot products with it. Right? So whatever the vector is that I want to apply this function to, that vector, what I'm going to do to that vector is I'm going to dot it with A. Right? So this function is linear. And very often we'll abbreviate this statement by just saying dot products are linear. And okay, well, when we say it's a little bit of a sloppiness of terminology. When we say dot products are linear, what we mean is with one side fixed and thought of as a function that you're applying to the other side, that function is a linear transformation. But again, it's a lot more syllables, and it's convenient to just say dot products are linear. How y'all feel about that? Is that cool? All right. So neat fact. Analogous fact. Cross products, again, thought of as a function. Cross products are linear. And that one seems a little weirder, a little bit less, a little bit more uncomfortable. And so if you're a little maybe not 100% sure you believe me on this, and by the way, don't just trust me, right? Go ahead and check this one, right? It's a healthy exercise. So you've got a definition of this function, and we have the definition of what it means for something to be linear, and you just have to check that this condition works. Ultimately, it comes down to just apply, write down what's on the left, apply known properties of the cross product operator, and what you'll find is that you get exactly what's on the right. Okay. All right. Okay. This last one. This one's a little bit of a weirder conversation. So we've got this thing D that's linear, and it's tempting to look at this and say, oh, determinant. Oh, okay, I guess it's determinants are linear. No. That is not what this says. We'll get to that in a minute. But D is not the same as this function. Let me first distinguish between the two different kinds of functions that we're talking about. D is a function that applies to a single vector, x. Here it is. X is going to be as I have it set up here, the last row of my matrix. So what does D do? D does a lot of stuff. D says, well, first I'm going to write down a whole bunch of other vectors to fill out the top part of this matrix, and then I'm going to take the determinant of the total matrix that I get when I fill in my input vector as just the very last row. So this is what D is. D is linear. Determinant is not that. Give me 2 seconds. Okay. Determinant, let me just for contrast. Determinant has a bunch of inputs. What is the input to the determinant function is the entire matrix. Right? Or you might say it as what's an input to the determinant is all of the rows. Right? And so if we were to claim that determinant were linear, we'd be trying to say stuff like, determinant of, A plus B. Does that equal to the determinant of A plus the determinant of B? And well, of course, that's easy counterexample, right? Certainly not. This is definitely not true. So determinant is not linear. It's only if I isolate just the one row there. Think of that one row as the input. Everything else is fixed. These rows up here are not allowed to change. They're part of the definition of what this D function is. That function of just the last row, is what's linear. Yeah, question.
So that's R1 to RM.
This is handwriting apology here. That's N minus 1.
Okay.
Yeah, sorry about that. N minus 1. Yeah. So I needed this matrix, of course, to be square so that I can talk about determinants of it. And the vectors themselves have n elements. That means I have n entries in each row, and therefore I need a total of n rows. And so, yeah. Right. Okay. Sorry for the handwriting problem there. What else you got? Anybody else? So we don't want to mistake this for the false suggestion that determinant's linear. Absolutely not. But with the other columns all fixed and thinking of only one, with the other rows all fixed and thinking of only one row, as being the variable. That function is linear. So what we'll say, by the way, again, more sloppy but convenient math lingo, we'll say that determinant it's linear in the last row. And that's the suggestion that we're only thinking about just the last row as being the variable and everything else is set. There's another fact I'll point out, and you might have seen this in Math 218, you might not have, but there's nothing magical about the last row. It works in the second to last row, too. It works in any row. Take it at first row, middle row, whatever. It works in every row. And furthermore, it works in every column as well. Determinant is a very strange, very oddly convenient formula in a lot of ways. So it's linear in every row, and it's linear in every column in this sense. And because it has, this is another sort of a lingo thing, because determinant has all of these, kind of linearities in various senses, the word that we attribute to all of those properties together is we say determinant is multilinear. That's the word that they use, multilinear. And I imagine you haven't probably heard that term before. All it is a recognition that you have all of these different kinds of linearities. Okay. All right. Really useful facts. Okay. Last pause before we go to the next page. Okay. All right. So, last fact. Now, y'all may have seen this in Math 218. Maybe yes, maybe no. I don't know. I think this is extremely important. But if you're looking at what I call Euclidean functions, right? So that the domain for the function is Euclidean space Rn. The target is Euclidean space Rm, whatever. Among Euclidean functions, if you have a linear transformation, a Euclidean linear transformation, then there is, by the way, side note, quick pause, this is math shorthand, backwards capital E, and it means there is or there exists, something like that. So there is a matrix A that allows me to compute that Euclidean linear transformation as a matrix product. So another way to say this is that every linear transformation fundamentally is a matrix. Now it goes both ways. Going the other way is kind of less surprising. Going the other way, every matrix is a linear transformation. You can just check that immediately. Just take this formula, plug it into the formula to the property on the previous page, and just multiply it out and confirm that sure enough, matrices do have that linearity property. And you can just crank it out. What's surprising is that every linear transformation is a matrix. And what I think is really most surprising, this is my opinion, what I think is most surprising about this is that this word linear transformation it's just a property. It's not constructive. This isn't telling you how to compute your formula or whatever your t is. But I don't know how to compute t. And yet, the mere fact that it has this feature, all of a sudden, I do have a formula for it. It seems like we're pulling it out of thin air. It seems like a no fair kind of a deal. But I'm going to show you how to prove this fact. By the way, quick show of hands. How many people have seen this fact before in Math 218? Very few. Okay, so maybe some modesty. So anyway, I think it's a really important fact, very important fact about linear algebra in Euclidean spaces. So let's assume that we have a linear transformation. We're going to see what we can conclude from that. And here we go. Got a linear transformation. Notice that every vector, now this is really, basic linear algebra. Every vector is a linear combination of the standard basis vectors. Let me just remind everybody, by the way, I know this notation is different in different courses. What is that thing? This is called a standard basis vector. The ith standard basis vector is a vector that's made up mostly out of zeros. There's a single one. That one is in the ith position. So we call this EI the ith standard basis vector. So that familiar? Perhaps, I mean, you might have seen these as IJK, different contexts. Okay. You run out of letters eventually if you do the IJK thing. That's why I like writing them as E1 through EN. You never run out. Okay. So anyway, easy to check. Any vector, whatever the coordinates of the vector are, I mean, multiply this out. There's your formula for the standard basis vectors. You multiply this out, and you will produce your original vector. So every vector, the linear combination of the standard basis vectors. Now, recall, I am assuming that I have a linear transformation. So I have this. I know this function is linear. I don't know a formula for it, but I know that it's linear. And linearity tells me that if I have a linear combination on the inside, I can rewrite that as a linear combination on the outside. That's what linearity is. Yeah? Now, so what? What does this buy me? Well, here's where I make a very clever choice. I'm going to choose, free country and all that, to take these things, the images of the standard basis vectors, right, the things that come out when you plug into the transformation, the standard basis vectors. I'm going to take those things, I'm going to give them a name, I'm going to call them A1 through AN. I'm going to make them the columns of a matrix. Now again, free country, right? This doesn't prove anything. But I'm going to generate this matrix. Now I owe you explanation of why I would do such a thing. What is this? What I conclude from doing this? But I'm just going to, choose to do this. And then now notice what happens though when I do this formula that I had up here. Now keep in mind we were computing. We were computing t of x for no apparent reason. I had that. And now, keep in mind, I've got this choice that AI is my new notation for the images of the standard basis vectors. Let's just plug those in. And oh my gosh, I have a linear combination of the columns of a matrix. Where have I heard that point of view before? What is a linear combination of the columns of a matrix? Here it is. A linear combination of the columns of a matrix is a matrix vector product. Right? So this is a really important point of view on matrix multiplication, right? I mean, this is the foot in the door that allows me to recognize that what I've got here is indeed a matrix product. And so we win. Let me kill the color coding here. Altogether, what I have now shown is that the linear transformation is computed as a matrix vector product. And furthermore, not only that, but I have an explicit formula for my matrix. My matrix is the one whose columns are the images of the standard basis vectors. Everybody good? I think this is a fantastic proof. I really love this proof. For one thing, this is a really important fact to know is that, when you're in Euclidean space, which we pretty much are going to be in this class almost entirely, linear transformation means matrix. Very handy. Right? The other thing is that this proof This proof uses a lot of fundamental facts about linear algebra. It uses the definition of linearity. It uses this key property of standard basis vectors, and it gives you the explicit formula for how to find the magic matrix. It does what we want it to do. Okay. All right. Real quick, last thing, and then we'll. Oh gosh. Okay. Well, anyway, I never cover as much material as I think I'm gonna cover. But we'll call it a day right after this. Another point of view on matrix multiplication. Kind of a weird formula if you think about it. That whole dot product thing, rows, dot columns. Who dreamed that up? How strange. Surely we could have dreamed up a easier formula, right? Linear combinations of columns. Okay, that's nice and all, but again, kind of arbitrary seeming. Why not linear combinations of rows? Why columns? Well, here's a pretty crisp answer to that question, I think. If you want to understand composition of linear transformations, right? This is an extremely, indisputably natural move. I've got two linear transformations. I want to do one, and then after that, I want to do the next one, right? I want to concatenate these two linear transformations. Very natural construction. What that corresponds to from the matrix point of view is matrix multiplication. So this is my crisp answer to the question, why do we multiply matrices the way we do? Well, we do it the way we do because that's the only way to do it that makes matrix multiplication correspond to composing the linear transformations that they represent. Okay, so I think that's a really important fact. Okay, we're drawing the line right here for today. Sorry to go a little over. We just finished section 1.6. Let me remind you that on the, let's see here. Let me go to the lecture schedule. Here we are. So here's the lecture schedule. I'm going to be filling in right here for today's date. You see here's today's date, Monday, August 29th. The sections assigned in that column there is going to be just section 1.6 because that's all we finished today. Now, on Wednesday, that's going to be here instead of here, right? But it's still part of homework assignment number 1. On Wednesday, we're definitely going to finish 1.1 also because that's super quick. And hopefully, fingers crossed, hopefully 1.2. So anyway, look for these updates on the lecture schedule. Y'all have a good day. See you on Wednesday.